Hello, good morning, everyone. Welcome to Cox.com learning series with Python fixings. As we are getting people through, feel free to say hello in the chat. Share with us your name, your position, your title, and the company you are tuning in from. Would love to see where everyone is joining from. Um, while we are doing that, I am going to do a quick intro and then we'll get started. We'll have Robert today to share with us on the topic of Hollowcore Anchorage. All right. Hey, Bruce. Good to see you. Philip, just quickly share my screen. My name is Ati, joining in from Calcs.com, or formerly known as ClearCalcs. We are a software platform for structural design for residential, commercial, and light commercial and industrial projects. So the way that we help engineers is we help you design and build something new that you might not have done before, or design your wood, timber, and steel. We have calculators across different countries and regions, most prominently in the US and Australia. We have a growing library in New Zealand as well. So if you are a user of Calcs.com, or if you are new to us, and if there's something that you want to see added to the library, please let us know. And the way that we work with structural engineers as well, we help you design with confidence. So that means for every design projects that you're doing, you know where the calculations come from. You can see the reference to formulas and standards for everything that you do, so that when you submit to a building reviewer, it is very clear on what you're designing and it is up to code as well. So in addition to the calculator library, we also are about to release a calculator builder. So this way, when your firm have a very specific needs or requirements on what you are building, you have internal knowledge or specifications that you want to keep for your calculations, you can then use our calculator builder to create your own calculations and templates and keep that across the organization in a standardized way, and something that you can share with everyone in the company without having or losing that context with as you do with spreadsheets. And then very soon as well, for engineering teams especially, we will introduce the analytics where you can view what projects are being done in what region, how many projects are being done across teams, and the number of calculations or the type of designs that you're doing as well. This is very useful to give you insights on whether you are over designing or how efficient you are in your design, as well as for manufacturers, for example, you can have a look at what are the most common products that are being used across the team. So that's a quick spiel on ClearCalcs or calcs.com. A quick housekeeping, if you have any questions, please use the questions tab at the bottom right of the platform. Post the questions and we'll go through that questions in order at the end within 15 to 20 minutes of the webinar. All right, Robert, I am going to hand over to you to take over the topic.
Cool. Thank you very much for that, Artie. Appreciate that. So as Artie notes, we're here talking about Hollowcore, Anchorage, and Retrofit, which is still, I suspect, on the front of lots of people's minds all across New Zealand. There's really, I guess the idea here is to be sharing knowledge that is practical and useful for anyone who is doing kind of any work in Hollowcore. There's three things that I want to cover, broadly speaking. The first is a section on C2 capacities on anchors, which is definitely a sore point for many people across the country. I definitely think it is still a undershared and undereducated topic. So we're going to go through a little bit of background on C2 capacities, what they represent, and things to be aware of when you're using them. So you have a little bit more information rather than just a spec sheet from a supplier with a number on it. The second section is going to be about some of the learnings we've had over the last 2, maybe even 3 years now, putting anchors into Hollowcore across New Zealand. There's a couple of things to watch out for in design that are worth being aware of, and some things that we've learned from contractors on site. And things to watch out for so you can mitigate them before you get to that point. And then the last section is on some of the work we've been doing in the retrofit space, obviously a hot topic. So I'll share some of that work so that everyone on the call at least has as many tools in the tool belt as you really can when you're looking at one of these buildings. Okay, so C2 capacities. Already mentioned a little bit about why we're doing this, so we'll just crack into it. As a little bit of background, they obviously didn't always exist. This is really where it comes from. So in 1994, there was a large earthquake in California in a place called Northridge. Many of us will already be aware of this. Prior to this, believe it or not, all post-installed anchor design and reinforced concrete was done using monotonic capacities in uncracked concrete, which I suspect everyone on the call will intuit is probably not the right thing to do. And as you might expect, there were fairly widespread failures of post-installed anchors in this event. Following this, the US put in place a 2-year ban, a blanket ban on any post-installed anchors and reinforced concrete in a seismic zone, which, as you might imagine, would be a pretty dramatic thing to do. And I mean, just imagine what would happen if we put a 2-year ban on a post-installed anchors and reinforced concrete here. The effect would be, I imagine, fairly dramatic. It wasn't until 2001 that it was able to be built into codes and standards, or a method of rating our anchors other than this was built into codes and standards. This was through the ACI 355 documents, which is the US testing standard, basically for concrete. And this was, it's called something else, but it's what we're familiar with as C1. It was actually originally taken from the Canadian kind of nuclear industry, who was using it for rating their anchors in the nuclear facilities. That's where C1 was originally developed. In 2013, the Europeans kind of came to the party and published ETAG 001. This is where we started having the scaled approach. So they started calling it C1, and then they also introduced C2, which is a higher level of seismic performance above C1. In 2016, the European Union basically just shuffled around how they structured their codes and standards, and they republished everything that we care about with regards to this topic under the EOTA Technical Report 049. Now, there's no substantial difference between this and the original ETAG 001 document. It's just changing how they publish this, but it's worth knowing because it causes some confusion in the industry where you see manufacturers publishing data based on EOTA Technical Report 049, and 3101 still references the ETAG document. They're effectively the same, but technically the EOTA reference is the correct one. In 2017, we came to the party and 3101 put that lovely sentence in Chapter 17, basically requiring the use of C2 capacities for any post-installed anchor into reinforced concrete in the country effectively, with some small number of exceptions. What is interesting is this really isn't where the story ends. In 2020, ICC, which is called it stands for International Code Council, but really it's an American certification organization, brought across C1 and C2 ratings. They called it ASP C1 and ASP C2 just to be a little bit different. And this was the first opportunity for American manufacturers to use this scaled approach. What is really interesting, in my eyes at least, I'm a bit of an anchor nerd at this point, ACI 355 committee last year, the year before last, in 2023, passed the new version of ACI 355, which completely removes C1 and only references C2. This is getting built into the US code in the 2026 revisions, so as of next year. The US will have completely removed C1 from their codes and standards and replaced it for C2 for any kind of seismic connection into cracked concrete in the US. There is a little bit of pushback in the US at the moment on this by a number of different consultants and manufacturers. but it's probably a little bit too little too late, and it's already kind of been improved or approved to be built into the 2026 code. So that's a little bit of background on kind of where we sit really globally around the use of these. It is getting more adopted, not less adopted around the world. To take a little step back on why we do this, this is a study that was conducted when they were first developing kind of the early testing regimes in the US. What they were looking at here was if you have a concrete slab and it starts to crack, like reinforced concrete slabs do, what is the probability that if you have an anchor in that slab, that crack occurs where the anchor is? And as you might expect, because we have a homogeneous material and an anchor which effectively acts as a stress raise, there is an above random probability. This makes sense because when the cracking occurs, if you have a stress raise, the crack wants to go on the path of least resistance, which is often where the anchor is. And this is really the basis for all of our kind of testing of post-installed anchors in concrete. We have this baseline assumption that when cracking occurs, it is going to occur where the anchor is. And this is actually probably a pretty reasonable assumption to make. There will be exceptions, but in terms of assumptions, this is probably a pretty good one. In terms of what we're allowing for, we're really allowing for three things. This is for C2 capacities. So we're allowing for cyclic shear behavior. I've got a little graphic here. This makes a lot of sense, right? If you have a reinforced concrete moment frame and you connect it to your wall, that wall is loaded in plane. Your anchors connecting the two are going to be loaded cyclically, not just monotonically, in shear. Similarly, if you have strong backs on a wall that's loaded out of plane, those anchors are going to be loaded cyclically in tension. And so we're testing for both of these, or the effect of both of these loading protocols when we do this kind of testing. The other one is the more interesting one, and this is really what differentiates, or one of the things that differentiates C1 and C2. When we're doing C2 testing, we're accounting for cyclic crack behavior. And this is when your cracks open and close around your anchor. And this occurs in many cases, but the clear one is if you have a reinforced concrete moment frame, and that is loaded cyclically in an earthquake, your reinforced concrete beam is going to undergo moment reversal, which means the cracks in that beam, which we're assuming are where the anchors are both going to open and close. And you can imagine if you start having a mass amount of concrete open and close around your anchor, that's going to have a fairly substantial impact on how that anchor behaves, and it does. What happens when we do this testing, we see it quite clearly. You start just getting concrete crushing all around your anchor, and as it crushes, you get more kind of concrete going in around your anchor, and then that doesn't let the crack close properly and causes more concrete crushing, and it basically just starts to disintegrate the material around the anchor. And this is a real mechanism where it happens. If you are getting kind of crack cycling around an anchor, this reduction that we're trying to represent at a C2 capacity is likely a very real reduction. Now, the other thing that I've got there is as you see down the bottom, a 0.8 mils. I'll talk about this more a little bit later, but basically the crack width that we allow for in C2 testing is 0.8 mils, which is slightly larger than C1, which is 0.5 mils. Now, to give you a bit of sense of scale on where the reductions in these capacities come from, and this is really a sense of scale, don't use this for anything, because it does vary a reasonable amount depending on what anchor type you're testing. But to give you a sense of scale on why this capacity is so low, it would be reasonable to expect when you're testing a good anchor under cyclic shear or cyclic tension, that you would be getting a reduction factor in the kind of 0.8, 0.9 ballpark, which is not too bad, right? It has a negative impact. Obviously, you're moving your anchor back and forth, but it's not a crippling reduction. The reduction for the cyclic crack width test protocol that you run for C2 testing, again, it depends on the type of anchor, but it would not be unreasonable to expect a reduction factor in the order of magnitude of kind of 0.2, 0.3, a huge reduction. And again, this is probably pretty reflective of what actually happens to anchors when they're caught in that crack cycling mechanism in an earthquake. And this is why our capacities are the way they are. Now, a little bit more info on this. Obviously, this has been a bit of a hot topic in New Zealand at the moment, and there was a kind of technical report ER, I want to say 95, that was published recently, basically suggesting that you should use C1 capacities for low risk connection of non-structural elements. There's a couple of other ambiguities that I think I will go through over the next couple of slides that I think are worth understanding and being aware of when you're designing with post-assault anchors and reinforced concrete of really any scenario, so that you're making sure you don't get caught out by something unexpected. At the end of the day, that number that you get as a C2 capacity isn't a magic number. It represents something. And so making sure that you are working within what that number represents is quite important. This image I have on the screen is the basis of that 0.8 mil crack width that we allow for in C2 testing. This comes out of another research study done in California. A lot of this work was done in California back when these things were first being developed, and is basically looking at what crack width we should allow for in a large seismic event. And the approach they took was they took a reinforced concrete beam. They excluded the plastic hinge zone because it's just too much damage to put an anchor into, which is very reasonable. Never put an anchor into a plastic hinge zone. And then they looked at just outside the plastic hinge zone. They took a fairly minimally reinforced concrete beam and estimated the crack width at the point where the reinforcing first starts to yield. They used predictive formula, and they came up with 0.8. Now, there is some discussion around the validity of this approach for different elements within a building. How does this relate to walls, floors, foundations, you name it? Putting that aside, the thing I think that's important to keep in mind if you're designing with this is if you are using a C2 capacity, the crack width that you're allowing for is 0.8 mils. Now, this is functionally useful when we do a design. If you are dealing with a kind of building where you're able to do a little bit more analysis, it can be practical to kind of do a bit of a sense check on what kind of crack widths you think you're getting in this scenario. If you're getting close to 0.8 or less than 0.8, then your C2 capacity is going to be conservative. If you're getting more than 0.8, then that would be a scenario where you perhaps wanting to put a little bit more thought into what you're doing and how you're using the anchors. Now, an important part of this, and this is something that we started investigating when we were doing this sort of testing, is how sensitive the results are to this parameter. How sensitive is our C2 capacity to the crack width that we use? Oftentimes, when we do this sort of testing, there are variables that we're looking at that really don't make a lot of difference, and you can vary them a little bit, and the outcome is fairly similar. This is not one of those. So the crack width is really sensitive to the outcome. If you have a crack width slightly higher than 0.8, your capacity is going to be a lot less, and similarly, if it's a little bit less than 0.8, your crack width is going to be a lot more. And so this is a really important thing to keep in mind when you're using these capacities. Now, the other thing that really makes a huge difference to the outcome, when this is again still looking at that crack width test, we have that width of crack, and we also have the number of cycles that we put the anchor through. We also have played around with the sensitivity of this, and similarly to the crack width, it makes a huge difference. If you have more cycles, your capacity drops. If you have less cycles, your capacity goes up quite significantly. Now, again, I'm not going to get too into the nitty-gritty because I think the important thing if you're doing a designer is just to be aware of kind of the significant things to be aware of. The basis for the number of crack width cycles that we do in C2 testing comes from a 90th percentile 475-year return period earthquake in Los Angeles. Now, what I have on the screen is basically the comparison of the acceleration spectra for LA, which is in black. The US code's a little bit different. They're looking at ULS and MCE, which is maximum considered earthquake. But for the point of comparison, it's good enough. And then we're looking at importance level 2 and importance level 4 buildings in red in different cities across the country. The thing to take away from this is a non-perfect match, obviously. Now, I don't actually have a good rule of thumb for you to take away from this. Where it is really significant is when we're dealing with, in our own designs in New Zealand, really long design life buildings or really long return period designs. And this is typically your kind of aisle for hospitals. It's worth really thinking about this. If you're doing critical structural connections in a IL4 building in New Zealand with a really long return period earthquake, there is a possibility that the cyclic crack behavior you're going to have on your anchors, depending on where that anchor is located in the reinforced concrete structure, may be more adverse than a C2 capacity allows for. It's pretty rare that that scenario comes up, but it is something that is worth keeping in mind because there are a number of possible scenarios in design in New Zealand where this could be the case. A more simple one. This links back a little bit to what we're actually talking about today, which is Hollowcore. Pre-stressed concrete in general, though. Pre-stressed concrete, which will be a shock to no one, does not perform the same as reinforced concrete. It's not intended to. When we reinforce concrete, the whole idea behind that system is that you get cracking in the reinforced concrete, which allows us to engage the reinforcing, so you get this lovely tension compression mechanism playing. When we have pre-stressed concrete, we have these pre-stressed strands in our concrete, which enables a cross-section of compression across the member, and that's how we're resisting the flexural loads. We're not relying fundamentally on cracking occurring in pre-stressed concrete. As a result, the cracking behavior is very, very different. All of the basis of a C2 capacity is allowing for cracking behavior in reinforced concrete elements. It really is not a good measure of how anchors perform in pre-stressed concrete because that cracking is largely what is causing the massive reduction that we see in C2 capacities and just doesn't happen in the same way in pre-stress elements. Now, unfortunately, the way New Zealand codes are written, we don't have a good out for this. 3.101 does just blanket say if you're in concrete, use a C2 capacity, assuming you meet the acceleration and importance level requirements, but most buildings do. But I think the useful thing here to remember, and there's other examples of similar sort of situations, the useful thing I think to keep in mind here as a designer is if you're putting an anchor into pre-stressed concrete, and you are by necessity using a C2 capacity, that capacity is going to have lots of redundancy. You can put that thing up to 100% utilization and feel very comfortable that that anchor is going to take those loads. So I don't have anything better for you, unfortunately, for that, but I think it is an important thing to keep in mind when you're doing these designs to understand what levels of redundancy you have for your anchorages in different parts of your building. Okay. That is really a bit of a summary on C2 capacities and some of the things I think are important to be aware of. It's obviously a very deep topic and can go a lot deeper than that. And then is the other side of what's going on in New Zealand at the moment with the ER that's been published looking at low risk non-structural elements and the use of C1 capacities. Feel free to reach out if you want to go into any more depth on any of that. It's one of the topics that I get quite passionate about after a beer on a Friday afternoon, and so finding someone who lets me rant about it is a privilege. Okay, next section, anchorages. So we've had some learnings over the last couple of years. We've put Hollowcore anchors, we've supplied Hollowcore anchors to buildings all across the country, and as with any kind of new developments in the industry, there's learnings. And so these next couple of slides are on some of the learnings. First two are on design, and the last one is some learnings we have from site and things to watch out for. Okay, the first one, shear loading in Hollowcore. After making a big deal about C2 capacities in pre-stressed slabs, you might notice if you've looked at any of our products that for our Hollowcore anchor, what we have on our published data is a C2 tension capacity and then an ASTM E488 shear capacity. This is not unique to our anchor, and this is why. So what we have on the top left there is basically the loading mechanism for a through bolt when we use the through bolt in Hollowcore. When we load it in tension, hopefully you can see my mouse. When we load it in tension, we have obviously a bearing connection on the top. Because it is a bearing connection and not a post-installed connection, we don't use C2 capacities. And that will have lots and lots of capacity that is really, really reliable because it's quite, it's not a post-installed capacity, so we don't and shouldn't use a C2 capacity. When we look at it in shear, again, it's a bearing connection. When we load that laterally from underneath the slab, what we're relying on here is a bearing connection between the steel shank and the concrete underneath the core, right? It's It's not a post-installed connection. We're not using C2 capacity. With a post-installed anchor, it's a little bit different. So the tension, when we load it in tension, that really is a post-installed connection, right? We're relying on that thread connection to the concrete. That's a post-installed connection. Following 3101, we use a C2 capacity. As good designers, we know in the back of our head that because this is a pre-stressed slab or pre-stressed something, we've got a lot of redundancy in that capacity, and we can put that thing to 100% utilization and sleep very well at night. The shear is a little bit different. When we load this in shear, the resistance from the shear loading underneath the slab is coming from bearing between the steel shank of the anchor and the concrete underneath the core. This is the same mechanism as with a through bolt. And this is not a post-installed mechanism, right? It's not a post-installed anchor mechanism. And so because of this, the C2 capacity is not needed. You're not relying on a post-installed connection in shear. You're relying on a bearing connection between the steel shank and the concrete underneath the core. Because it's a bearing connection, you get quite large capacities, and most people, when they supply it to you, will have downgraded those capacities quite substantially before they give it to you. And for that kind of scenario, the ASTM E488, which is a testing standard for anchors, is kind of the appropriate capacity to use. Now, actually, one more thing potentially on this, bit of a tangent. One thing that this does not apply to is when you use short stub anchors just through the underside of the hollow core into the core. Because you are relying on that post-installed connection both in tension and in shear, that is a post-installed anchor both in tension and shear. It is the fact that you have a gap between the post-installed connection and the point of shear bearing resistance that is significant here. And as another kind of side note, specifically for Hollowcore, I do recommend real caution when using short stub anchors into the Hollowcore. What we see happening on site is you only start with 30 mils of unreinforced concrete under the core, if you're lucky. And then to install any anchor, you're drilling up with a hammer drill because you need hammer action drills in 60 MPa concrete, otherwise you can't get through them. And so you get quite substantial and quite variable amounts of blowout on the inside of the core. It can often be as deep as 10 to 15 mils. And so you've started with 30 mils of unreinforced concrete, you've drilled through it, you've lost 10 to 15 mils of that embedment, and now you're putting a short stub anchor into it. And so your reliable embedment possibly might only be 15 mils and in completely unreinforced concrete because there's no reinforcing underneath the core. I've seen them go quite badly on site. They might be okay for really, really minimal kind of non-structural loading, but I would exercise real caution for any kind of structural loads into hollow core specifically, with short stub anchors only into the core for that reason. It's really hard to predict because the blowout's quite variable. The performance of unreinforced concrete in tension is very variable as well. And so the actual capacity you're getting out of those is really hard, really variable and really hard to predict. And in this scenario, really low. It would be a different scenario if it was reinforced, but when we're dealing with hollow core, it's not. Okay. Also on the topic of anchors and shear in hollow core, and this is there's a couple of examples where this is relevant, but the really clear one is if we've got transfer beams, diaphragm load transfer beams on the underside of hollow core units taking pretty substantial loads. There's kind of two ways we see anchorages designed for this scenario. The first is where you have a load at the bottom and then you take the load to the top. And the second is where you have load at the bottom, it carries up through the hollow core, and then the anchor helps it gets transferred into the topping slab. Hope there's lots of suspense there, but the correct one is the one on the right. And the reason for this is exactly the same as the reason that I have on the last slide. Anchors, while we think about them often as kind of rigid, low transferring elements, they're not perfectly rigid. And if you have a scenario like this where you have the steel shank across a gap, all of that load should be transferring at that bottom really stiff bearing connection location. Because that load is transferring there, that load needs to go somewhere. And so the way it gets transferred through the hollow core unit is in shear. And then in reality, your anchor is probably helping a little bit get the load from the Hollowcore up to the topping. Maybe that happens through some bond exchange, but either way, that's quite a competent connection. The reason I highlight this is we have seen scenarios where this part of this load path is the part that governs. So it is worth thinking about this quite early in the stage if you're designing a shear transfer beam in Hollowcore or kind of a similar shaped pre-stressed element or precast element. It's worth checking that quite early on because that can govern how much load you can put through these things rather than actually the anchors. Okay, next one, learning from site. While we have drawings of buildings all over the country that tell us we have minimum 65 mils of topping on Hollowcore units, as I suspect many of us on the call have found out, this is not always the case. In our very anecdotal experience, it's somewhere between 30% and 50% of all multi-story Hollowcore buildings. And it's a real annoyance. One of the reasons it happens is because your pre-stressed strands are quite low in the Hollowcore units. When they come to site, they come with a camber. And so they lowered them in, and then you pour your topping over top, and you have this, whatever your minimum topping depth is on the side, and it is not the case necessarily in the middle. And so it's quite often that you have less than 65 mils of topping. The thing to be really careful about is if you're installing anchors into this from the underside and you're not careful, or you just have not enough topping to make it work, you will start blowing through the top of your topping. This is a building, this is one kind of example where this was happening. On this building, actually, they were able to prevent it from happening if they were careful, but the contractor made the decision that it wasn't worth their time because they had, everything was out of the building, they had complete access to everything. And so they just went for gold and then came up and patched the top and then put their floor linings over the top. So that's a bit of a unique case. But often you obviously don't want to be doing that. The two things we found to work quite well. The first is just GPR scanning to ID really early on as soon as you have access to site whether or not this is going to be an issue. GPR scanners are pretty easy to use nowadays. You can rent them. You can buy them for not that much money if your company is happy to buy one. And they're pretty easy to use. You can go along. You can quickly find out how deep your topping is and just ID whether or not there's going to be an issue at all. From the contractor side, what we always recommend is drill stoppers. Drilling above your head hundreds or thousands of holes is really hard work, and you will get tired, or they will get tired. And then it's really hard to keep to the little piece of tape they use as a depth guide. A physical stopper is by far the best option. And then the other side of things is just to go and do a range of trials when you first get access to the building. So figure out what's going on in the building, figure out the minimum embedment you need for your anchors, go try drilling it in a couple of locations. We have seen one contractor use they built a rig, they built an automated drilling rig, and that was really, really effective. Once they did that, they stopped blowing through the top. But of course, that's a little bit of effort, and so that's not necessarily justified on all jobs. But that is a thing to really be aware of when you're doing these buildings. It is a risk. Cool. The last section is on retrofits. Despite having a picture of the steel strongback retrofit on the right there, I'm not going to talk about steel strongbacks. There's been lots of kind of communication around that by people much more knowledgeable on it than I am. What I'm going to talk about is kind of the research that we've been doing in this space. If anyone kind of knows Python, we quite like full-scale testing. We get a kick out of it, and we think it's really useful. So I'm going to share a little bit about what we've been doing in this space. These are snips from the recast floors, or one of the many recast floors papers that was published in the CSOC journal. I really liked these graphics. What they were looking at here is basically alternate ways to address the four failure modes that A, they're concerned about, and B, the steel strongback retrofit addresses. And that's obviously loss of seating, shear failure of the floor member, positive moment failure, negative moment failure. And you see here, they're basically using a combination approach. We've got cut and tracing of bars to address the negative moment failure. You've got supplementary positive moment reinforcement on the underside in the form of FRP. And then you have your seating angle, of course. And the way they've done their supplementary transverse reinforcement or supplementary shear reinforcement is post-installed anchors and then transverse PFCs across all of those lines. Now, we basically went around when this first started coming out, talking to contractors we knew and other design engineers, basically discussing this as how feasible this was an option. And the general conclusion was, because of all the PFCs, and if you start doing the math on, say, a 10-story building and 4 to 10 PFCs each side of every Hollowcore unit in the building, things scale out of control very quickly. The basic conclusion was that because of the PFCs, you may as well just do the steel strongbacks. And so the work that we've been doing is basically looking at whether or not we can get rid of these PFCs. And this has kind of been built into the anchor design that we've done in this space and the testing that we've done in this space. This is one of our test setups. There's been a couple of different ones now, but this is quite a good photo. We were putting kind of 400 kilonewtons through this thing, which was a lot of fun. This is basically, we're just doing A/B testing here. So what we're looking at is looking at as-built performance, and then with post-installed anchors, and looking how those post-installed anchors behave when they're installed as supplementary shear reinforcing, and looking at whether or not that's a reliable mechanism that you would be able to use, rather than additionally adding PFCs along the bottom. And so what we're really caring about is how kind of the heads of the anchor perform and hold the underside of the Hollowcore unit, and whether or not that's going to be a reliable mechanism. This is one of the test program's results. What we have on the left there is just an A/B test from 2 of the tests, looking at the black line being the as-built test and the green line being the post-installed shear reinforcing test. You obviously get an increase in shear capacity when you add shear reinforcing, which is really what you would hope, which was very promising. That bottom right photo is really at the end of that HC2 test, which is the green line being the retrofit test, looking at the failure modes that we're getting. And so you can see there that when we take it quite far, we are still getting shear failure in the concrete, which is positive from the point of view of using anchors without PFCs. In this scenario, PFCs wouldn't have had a particularly large additional benefit, right? You're still getting that concrete failure. You're getting an increase in shear performance from putting supplementary shear reinforcing in, but you're not getting this kind of mass pull through of the heads. And part of the reason is that we have these really large heads on this anchor specifically for this scenario, so you're able to prevent this kind of pull through mechanism. What else I thought personally was really useful in this, really interesting in this research, the as-built line, you can see you kind of get your peak shear capacity, it fails, and you kind of get really flat, constant post-failure shear capacity. This is coming entirely from strand pullout. And you can see in the top right-hand corner, that's one of the strand holes in the Hollowcore unit, and you can't even see the strand anymore. It's pulled so far through. I mean, you can see we kept the displacement going. What's that? Nearly 30 mils past failure. We just kept loading the thing, and the strand just slowly pulled out. You can't actually rely on this, or the guidance is not to rely on this in design. The rationale, it's pretty reasonable, is that that's surrounded by unreinforced concrete, and so you can't reliably say that unreinforced concrete is going to stay in place. The whole thing could just break away. But I thought that was really interesting, and seeing it happen, that strand pullout is a real thing. And if the concrete didn't break away around it, it would be really useful. But unfortunately, it's probably a reasonable assumption to assume that unreinforced concrete is going to break away a little bit. Okay, some of the just kind of the really interesting things when we start seeing this used in the industry. So this is a building in Wellington that basically went through that process of using basically our anchors in place of having mass PFCs on the underside as your supplementary shear area. You can see on the top they've got these cut and chase bars. On the underside you've got your supplementary seating, and then Python anchors as your supplementary shear reinforcing. And that's just kind of the floor layout. What was really interesting when we went to start and talk to this contractor, they were telling us that, putting aside the difference in the cost in the retrofit, which was profoundly large, just the fact that they didn't have to take down all of these services that were in the building, suspended services. When you're doing something like steel strongbacks, you have to go in, you take all your services out, or at least the services at the end, normally all of them. You put in your retrofit, and you put all the services back. They were saying because they were able to get in without taking the services down, it saved them about $500,000 per floor. that's a 15-story building. That's $7.5 million, not from the difference in the retrofit, but because they're not having to remove the services. And that was a bit of an eye-opener for me, because that's not really what I'm thinking about when I'm doing my retrofit designs. I'm trying to optimize the retrofit. But it can be really good to think about these more kind of broad impacts of what we're doing, because that is $7.5 million off the cost of a project is a profound amount of money to be able to be saving on one of these projects. Okay, that is basically what I wanted to cover. I see we have a couple of questions in the chat. If anyone else has any, you're very welcome to put them in the chat, or unmute yourself if you like to, but perhaps I'll start with what we have in the chat, and we can go from there. So the first one is start live answer. Okay, can uncracked concrete be considered for anchors in pre-stressed concrete? So there's a couple of approaches to this. The first being what our codes say, and 3101 basically says no. All post-installed anchors should be designed in accordance with kind of the ETAG documents. And the basis for using C2 is a combination of ground acceleration and equivalent to something different in the Euro codes, but it's equivalent to importance level. Practically, possibly, I see it done in reinforced concrete as well. If you're able to demonstrate that you're not expecting any meaningful cracking in your reinforced concrete, whether or not it's by FEA or anything else, I know that gets accepted in council. And from an engineering point of view, if you're not getting cracking in the concrete, and especially not that cyclic crack behavior, then a lower rated performance category would be completely appropriate from an engineering view, in my opinion. But there is a little bit of that duality going on there, because we're quite lucky in New Zealand that we have the alternate pathway. You do have methods for taking that approach. But technically speaking, from the verification method, it's very uncommon where that would fly. From Ben, is the drilled hole oversized to accommodate the threads of the screw? How does it affect the shear capacity? I'm going to go ahead and assume that you're talking about the pilot hole in Hollowcore. So the way that we make screw anchors is called cold forming. So basically you get wire. The wire diameter is the diameter that we describe it as. So if we're making a 10 mil anchor, we have 10 mil wire to begin with. And then what happens is you have these really large machines with tools, like shaped, threaded pieces of steel on each side, and they roll the threads on. So it's literally cold forging the threads. Basically means that the inside of the thread becomes less than 10 mils in diameter, and the outside of the thread becomes more. And so when you drill your 10 mil diameter pilot hole and you install your anchor, your unthreaded shank portion, which is, if I go back, the unthreaded shank portion is 10 mils, and it is snug in a 10 mil diameter hole. And so you're getting very good immediate engagement in that scenario. I think that's what your question was. Maybe put another one if I misunderstood that. For Trev, for our tests, so our tests were like this. And so what you've got on each side is a pinned connection. If I had unlimited, sorry, the question here was, were Hollowcore seated on walls or EBFs, and considered your test results, or just beams? We idealized it as a pin connection on each side. If I had unlimited testing budget, I would build one of those amazing full-scale assemblies that the Christchurch University did. But I do not have unlimited test budget, and so the balance we struck was pin connections on each side to allow for rotation at the ends. From Ben, did any of the wide heads pulled through the soffit flange as part of your testing? If so, at what stage? Not completely at the point of failure. And so you got a little bit of engagement from the underside of the Hollowcore unit. And then it takes the load, and then you're still getting kind of the failure in the concrete and the movement in the concrete, which is really triggering that initial shear failure. And then what happens, if I go back to the results, is the anchors re-engage and then take a little bit more load. And then when you're about here, that's when we're starting to get the anchors failing as anchors. So you're losing your, normally it depends on which variation of anchor we used in the testing. We had a couple of variations, but you're either going to pull through the heads or pull out of the threads. But that is actually quite a bit past that main initial failure that we see. For Stephen, rows of shear reinforcing looks quite large in the photos. Is this any different to recast floors guidance with PFCs? I don't think the guidance would be any different. I didn't do the design for that building. I'm not 100% sure what the spacing was governed by, but fundamentally it should be exactly the same, right? We're not the only thing that's changed here is getting rid of the PFCs. The same philosophy behind how you design that shear reinforcing is exactly the same. From Bruce, do fixings for seismic restraints could count as C1 or C2? This is a fun one. So technically, following 3101, basically any post-installed anchor into concrete in a building that is above the ground acceleration requirements and the importance level requirements, which is the vast majority of buildings in New Zealand that we hear about, the code says C2. However, there are some impracticalities here. And so that new kind of guidance has been published by a number of key people, mostly designers in the industry. It's called ER95 if you want to look it up. It's called Code of Practice for the Seismic Performance of Non-Structural Elements. And it's a little bit of an effort, my understanding is, I was not involved in writing it, but it's a little bit of an effort to take a slightly more practical approach to the low-risk non-structural elements. So for anything that's kind of still above people or high weight or anything like that, it doesn't change anything. Our codes say you should be using C2 capacities technically. But there is now some formal documentation from that report for what is deemed, and they have guidance, if you read it, around what they classify as kind of low risk scenarios for non-structural elements where they recommend using a C1 capacity. So if you're doing that kind of work, I would recommend just going and reading that document. It's very well written and quite clear to understand what their intent is. Cool. That was everything in the chat. Anything from yourself, Artie?
No. If there are no more questions from the audience, I'm happy to give everyone 10 minutes back of their day. As usual, we will send a quick email after this asking for your feedback, and you will receive a recording of this webinar as well. We will also be sending a couple of follow-up resources from this webinar to you, as well as Rob's contact details if you want to reach out to him or have any specific questions that you want to discuss. Rob, thank you so much for your time. I appreciate you sharing with us about this today. And everyone, thank you for joining. Hopefully you learned a thing or two today in this session.
Yeah, thank you, Artie.
All right.
And thank you all for dialing in.
See you, everyone. Have a good day.